Whenever you're ready,
Yeah, good thing I got here 20 minutes early.
yeah, yes. There's always glitches.
Yeah, my machine for some reason wasn't loading things correctly, so we just put it on there.
Okay, very good, thanks. Okay, so let's get started. We have Jim Alves Foss from University of Idaho, Director of the Center for Academic Excellence in Cyber Defense at the University of Idaho. We're glad to have him on the team. I'm going to let him go ahead and start talking.
All right, so we're going to be doing hands-on stuff. So log into your AWS Linux workspace as you can. No, nothing specialized. If you got your Linux laptop, you got a virtual machine on your laptop, whichever way, all that works fine. All right. So this is binary analysis 101. Just how do we analyze executable binaries using standard Linux tools? I don't know how much background all of you have in this area. I suspect it's a mix. So this is going to be hopefully not too basic for some of you. Actually, I should ask, how many of you are intimately familiar with assembly code? All right. Binary analysis.
I wrote a bootloader, so.
Hey, wrote a bootloader, you win. And using Linux tools and stuff, we'll see how it goes, and we'll see where we get with that. So, first, a related topic. You've already discussed forensics in the workshop. With respect to a host-based forensics, not network-based or media-based, why do we do forensics? I'm looking for three very broad descriptions of how the computer played a part in the incident being investigated.
Attribution.
Attribution, explain.
You have binary executables with.
Well, forget binary executable, just general forensics.
So you need to know where it did, when it happened, if there's a time correlation with it.
Okay, so you're analyzing for malware doing something to the computer. I want very broad.
Okay.
What else? Anyone?
Gather information.
Okay, but broad, what role did the computer play in the incident? I know I'm stretching. I haven't told you guys what I'm looking for. It's one of those hard questions. All right, I'll start with the first one. The computer was the victim of an attack. Somebody did malware. Somebody launched something. There was an advanced persistent threat, and they logged into your system for the last 6 months and doing something. And you want to figure out what the bad guys did, when and where and how to my computer because I was the victim. But what else could the computer be besides a victim in an attack? The tool to do the attack. So the computer was used as a weapon to launch the attack. What's the third thing?
Just a stepping stone.
A stepping stone, or basically it was used as a tool to store and access digital information related to the attack. You know, this is where, hey, we seized the computer of this drug dealer and he kept an Excel spreadsheet of all his clients. We got his email, you know, we got the porn they're storing there, whatever. The computer wasn't actually used to do the attack, but it was used as a digital repository. A lot of people I've talked to in the past think there's, you know, oh, it's a victim attack, and that's all they focus on. They don't think about the other aspects. I want you thinking about the other aspects. I want you thinking about different ways of looking at things because cyber is not one thing. All right. So now when it comes to binary analysis is the act of evaluating an executable program or a set of related programs and libraries to determine characteristics of that program, usually cybersecurity related. So again, I want three broad categories of sources now. Sources of binaries we may want to evaluate.
So what do you mean by sources?
Where'd they come from? Who created the binary?
All right.
Anyone?
Well, image files.
Okay, not where it was, but who created it?
Yeah, it's created it. One possibility is that it was created by an attacker and distributed through emails.
Right, so created by an attacker. So basically the binary is untrusted and they contain malware. And so we want to look at the binary and say, hey, What's the bad stuff in here? What's it doing to me? Is it a virus? Is it used for ransomware? Is it, a worm or something else? But and there's a whole groups of people. That's all they do with binary analysis. We're going to look for malware in this binary, but that's not the only thing we do with it. So what else can we look for? Or what other type of binaries could we have if they're not possibly malware?
Trusted but vulnerable.
Trusted but vulnerable, and there's two classes of that. It's developed in-house, but we need to evaluate it for security vulnerabilities. I built this software, but I need to evaluate it as built. I wrote this, the source code, and I think I know what I'm doing, but I don't. And then there's an executable and evaluate it. Or the other one is a third-party vendor. Somebody else created the software. We kind of trust them that it doesn't have malware in it, but I'm going to incorporate it into one of my systems. And it needs to be evaluated for security vulnerabilities. And so these are the reasons why people look at the binaries. Now, where do we do this? Well, capture the flag competitions, they do binary analysis all the time. It's really fun. How many of you are familiar with the distinction between little endian and big endian number format? Most of you, not all of you. Okay, so if you have a 4-byte integer, little endian, the least significant byte is stored first in memory on up. Big endian is the opposite order. There was a DEF CON capture the flag competition where they had 3-byte integers with middle endian format. So the least significant byte was in the middle of the 3, just to mess with you. It was a customized, simulated, processor. Nobody would do that in reality, I don't think.
Well, middle engineering was used on like certain ARM processors.
There you go.
Which never used to.
Yeah. Bug bounties. So, hey, I go out there, I find, HackerOne or some other website, and I analyze software and I find a vulnerability and I submit a report to them and they pay me money. White hat ethical hacking, somebody hires you to just pound on their code. That was discussed in the talk on the life of a security expert the other day, last week. He talked about, hey, people hire us to analyze their code. There's also certification of software. We may hear about this at Keyport tomorrow or Friday. I know I've talked to people who've worked there before who said, basically, vendors bring us software. We want to make sure this software is safe before, as the one woman put it, before it affects my sailors on my ships. She was very possessive. I need to certify the software. And we were actually on some interesting phone calls with her several years ago. There was vendor created this real-time operating system software, high assurance, multi-level security, so it can combine top secret and secret stuff, and the twain will never meet. And it was all built on a single core processor. Then Intel came out with this multi-core processor. You think the Intel Duo, so we're talking a long time ago. And they said, oh, we'll just run it on that. It's the same thing. And she said, no, it's not. I need to know what that other core is doing. Show me what your software is doing. They said, oh, it just turns off the other core. She says, I don't believe you. So we called up Intel. We were on a phone call. NSA, woman from the Navy, actually, we didn't have the vendor going. Myself and a couple other people. And they called up the guy from Intel. Hey, so what is the command you use to turn off the other core? And he goes, what? What is the command you do to turn off the second core if you don't want to use it? I don't understand. Why would somebody want to do that? I said, well, you have a core. We're not using it. We want to make sure malicious software is not running on it. What? Malicious malware is not running on it. So how do we turn it off? He couldn't figure it out. I mean, ultimately, it was in the BIOS. She didn't boot it up. It was a solution, but he never thought, we gave you a second core. Why wouldn't you use it? We build it, you'll use it, right? That's the way modern software and hardware technology works. We build it, they'll use it. Security will come later. So that's another place. So we were doing a lot of binary analysis on these real-time operating systems for them. Also, there's a DoD hard problem list. They want automated response to attacks. I'm watching the system. The system's under attack. I detect the attack. I want to automatically scan the software that was attacked, automatically patch it when the attack was detected, without breaking functionality or performance. And I want to take it a step further. I want to do automatic proactive security. I got stuff running on my system. I want to be able to scan it, patch it before attack. Automatically, knowing nothing about the software. The DARPA Cyber Grand Challenge showed that that was doable. Now, it was started in 2014, went for 2 years. The winning company was now funded lots and lots of money from Department of Defense to do this. They created a system they're calling Voltron. And I forget the other, Castlegate or something like that, I don't remember. Bonus points if you can automate the attack, the government says. Cyber Command says, hey, you find a vulnerability in the software before we know what it is, give us the way of taking advantage of it so we can own our adversaries' computers and also protect our, scan for that attack, protect our own. These are all things people are trying to do. So how do we do this? The main thing you want to do is develop a binary analysis methodology, an approach to doing these things. I'm going to give all the credit here to Matthew Bourne, his binary analysis cookbook, Packet Publishing 2019. He has this GitHub at the bottom is a list of all the samples from there, the book. It also has a link to how you can get the book. I think it's $10 right now, Packet Publishing. You want to perform, and I'll talk about each of these steps as we go, but you want to perform binary discovery, find out where executables are in the system, gather information about them, do static analysis, dynamic analysis, iterate, and then, oops, that's a typo. Automatic methodology. Anyway, automatic. You want to make things automatic. Why do we want to make things automatic? It's fast. The attacks are fast. Our adversaries are automating things. We've got to do it. Now, some people, and if I talk about the Cyber Grand Challenge, people believe, oh, that's artificial intelligence. You developed an artificial intelligence technology to find the vulnerabilities. Not really. That's not, it was a bunch of heuristics. It wasn't true AI. And it was multiple. So we were in the Cyber Grand Challenge. They gave us a rack of 20 Xeon servers. I ran 1,600 VMs. Now, 1,200 VMs simultaneously to run the multiple analysis on the different binaries. I didn't need to. I just did because I could. Because we have a lot of compute power that they gave us for free. All right. So, get on your Linux workstation, type the following. First, sudo su. Now, for those who don't know, sudo is super user do. It's basically allowing you to execute something as super user. You type su to become super user, the root, the administrator count, then you'll have to type in your password. The only reason I'm having you do this is because we want to search for things that you don't have permission to see as a normal user. And then you run the find executable. Let's see. We're going to type F for finding executable files. So the find command searches, searches the directory you specified, which is the root directory here, find executables files. So if I go to mine, oh, great. Good, can't see my password. And I typed it wrong, I can feel it.
Like ELF file, going to find.
It's going to find a lot of things.
Yeah.
It's okay.
Find just JavaScript.
It finds a lot of things. Yes, we're going to work on that. So let's see. Find / minus executable minus F. Whoops. Oh, let's try that again.
Find
Oh, that's my old password. Let's go back here. Where to go? Show you, where's my PowerPoint? There it is. There's the command again for those who didn't see it. Now, it's going to give you a list. Okay, so let's try this again. I'll get this password right one of these days. There we go. So find / minus execute.
I've also found it very difficult to type in through password.
Uh,
I can't type it in. Neither can my
minus
opponents.
Get something wrong there. Minus type F. I got one too many windows here open. That's my problem. And so these are finding different executables on the machine. Okay. What I wanted to point out, there's a bunch of my home directory. It's finding my own executables, as well as past all those system ones. So there's just one way of looking for and finding, things on the machine. Then you can type the following. Okay. File. File is a command. So find is a command that can help you find things on the machine using different pattern matching, different attributes. Use file, it tells you information about the binary. Now I've got two different versions here. One -I, which gives you a little information, and without the -I, that gives you a lot more. It gives you more information. I won't say a lot more. So hear that. File -I. Cat. So it says bincat is an application, executable, character set binary. If I do file / bincat, it tells me it's an L64-bit LSB executable using the Intel 64-bit version 1 application binary interface. It's dynamically linked, use shared libraries, et cetera, et cetera. It even gives us the SHA-1 hash of the binary. So there's different things that we can find with things like find or file. And you can also do the ls to just list things. Notice the sort order in this one when you do this one. Tell me what it is. Sort order. That's not -alt, it's -ALT, 3 different options. So that's -alt / bin. And all of these are all the executables in the /bin directory. And they're sorted somehow. It's not alphabetical, as you can tell. It's by date. It's by time, technically, of when it was created. So there are ways of searching and looking for things, specific dates and times, and getting that information. Now, I'm going to throw in an extra command, -WC or WC word count. So there's 1,304 binaries with lines here, binaries we found here. This is the number of words and this is the number of characters. And so we found 1,300 of them. That's pretty good. Let me go back up to the other command. Notice, for those who don't use Linux normally, notice how I'm quickly stepping through the commands here. Actually, let me clear this. I'm just using the up arrow, and it goes through previous commands. That's a useful thing to have. If I do the find, okay, it said a permission denied one. There's 6,776 executable files found on this machine.
51,000.
You got 51,000, yeah, your own machine.
But apparently, it's considering things like ping images,
Yeah.
CSV files.
Anything with the executable permission, it's set. Just what it's doing. All right. Now we want you to try the following. There's another way of finding things. You use the locate command. You may not have locate on your machine. If you don't, you could type yum install mlocate, and it'll install it for you. Hopefully, you have permission to do that.
APT installed first.
What?
You wouldn't want to do them. You want to do APT installed.
APT is not installed in these Amazon workspace.
So,
Thanks.
okay.
So you could do an apt install APT. You're using a different machine. But yeah, app's not installed on, or apt-get is not installed on there. And then you could do an update DB and a locate cat. Now what's interesting, so update DB updates the locate database. Locate cat then helps you find it. So if I do this, I'm gonna have to do install, and you have to hit a yes. It doesn't take long to install. Update DB, that doesn't take long. Then locate cat. And there's a whole bunch of programs with cat in their name, which is unfortunate for me. There's what? 5,392 with cat. Another command I could use is just, I could do where is cat, and it tells me it's user, it lists two things, the man page and the actual executable. Or you could say which cat to tell you which one it's running. Where is tells you all the ones that are available, which tells you which one takes priority. So we have lots of abilities to find things here. And this is another one, PS minus EF. PS is process status, shows you all the programs running on your machine. With the minus EF gives you some additional information. Now, I'm showing you this, which I haven't shown you before, the pipe more for those who aren't familiar with that. The pipe command says take the output from here and send it to the more program. More shows things one screen at a time. You can hit a space bar to go to the next page, enter or return just to go one line at a time, Q to quit, question mark for help to show you all the different more commands. Or some people prefer less instead of more. And if you like less, you can use the H for help. Because some of the commands are different. But if you do a PS, so this one, we'll see I have all these root programs running, lots of different names for them. I've got a couple other owners, Cronny here, Polkit D. And then finally, I've got my stuff and the different programs I'm running. And you can see some of the names of the programs that are running. And so this is just another way of finding out what's going on the machine. So this is all just exploring the machine, finding out what's running. Oh, somehow this got off. Okay, somehow my order got it wrong. Let's do this first one. This is a harder one. What this does is it finds the executable files, loops through them, greps them, which does a pattern search to see if they're executable binaries, and gives you that list. I don't like this way of doing it. This is the way folks suggested, so I do that. I have my own ways of doing things. But this does one file at a time. So that's a longer one. I did email all these slides to Gabriel, so hopefully they'll go up on the agenda. There we go. Schedule. That's what people have. But again, you're going to see a lot of different executables on the program thing. But now we're only finding the binary executables, not all the scripts and other things. Hopefully. I'll wait till everybody gets further along. Well, not that long, actually. I know you're probably trying to still find it, aren't you? Well, let me put it this way. On your machine, it may take longer. This one, the default, oops, copy. Copy. Oh. Paste. So it takes a little while. Like I said, there's, oh, what, over 3,000, 5,000, you got 50,000, so. But these are all the executable ones, and you can find all the planes. Now, I'm noticing a dispute image. I don't think that's executable, but it's binary. So it gets us closer to what they are. There's other ways of doing this, but this gets us close. So I'll stop it. Control C can stop the command. Now, I'm typing exit here. Why am I typing exit? I don't need to do anything more right now. So I want to leave my root shell and go back to a normal user shell. Why? You don't want to operate as the super user or root unless you absolutely have to. I've seen too many things, like the Darkness Cyber Grand Challenge, they actually made us run everything as root. And it's like, we're talking about binary analysis of potential malware and vulnerabilities. No, I don't want to run as root. Why? Well, that's just our default. It's easier. Yeah, no, you guys are supposed to be the experts. You're supposed to know better. So we reconfigured it so we didn't have to run things as root, except when we had to. But this, because we were talking about this earlier about executables, I'm going to look at this one file. Okay. Clear my screen again. Now notice when I'm typing this, I type D, and then I got the whole thing. Tab, auto-completes for you with Linux if you're not familiar with that. I have so many students who don't know this. Okay, it's a Python script. So if I actually do a more and look at it, notice the beginning has this command. So the pound exclamation says, hey, use this as the interpreter for the rest of this file. So that's how it knows it's a Python script. You can have bin bash. There's also like use a local environment Python for a different way.
About the shebang character was whether or not when it gets sent to that program, it's going to read only use this with languages that actually treat the shebang as
A comment.
As a comment.
Yes, or and deliberately parses it out. Yes.
Yeah.
And of course, you're supposed to. You should have like -i for interact or some other things in here because the string just
like
bang is potentially some problems with
I
that.
think like Node.js will actually ignore the shebang.
Yeah.
Even though it's not strictly a comment.
Right. So they built it in because people have been using it. But this is how that program figures this out. If it's using, I'll show you a different one later, how it figures things out. So, and the more again, you can, instead of typing things more, you just use more to list something. Again, it does one page at a time. So we have different executables. We have different types of things. The first thing we want to do when doing analysis is find them. That's what this is all about. Are we good? Do I move on? Some of you are lost. Okay. The which program is running? We can say which bash, it tells us which one it is, or where is. You can even see which commands and aliases are available to you to execute by using compgen -ac, lists everything that you can execute. But we can do manual pages, man find or man file. I can even do those. And again, I've had enough students who don't know this. So I go to here, I can go and Google man find, and I can do the Linux man page for find. I don't have to be in a Linux browser to do it. I can just do the manual page in Google, which is really nice. So I'll have one window open on my login, my terminal, whatever, to my Linux machine, another one on a normal window where I have my browser. It's all there. It is so different than it was 40 years ago when I first started learning this stuff. So, like, try the compgen or the which, where, try those. If you're not familiar with using these command line tools, you've got to become familiar with using them if you're going to do any of this type of work. GUI interfaces only take you so far. And Yes, even though the mouse and the windowing technology was built in the 70s, it took a long time for people to actually have to use it. Yeah, it wasn't invented by Apple. Who invented it? Xerox at the Palo Alto Research Center. Yeah, I don't remember the name, of course. All right, now we have an idea how to search our system for potentially malicious binary. We're finding the executables. Let's focus on what we can do to gather as much information about that executable as possible. So like penetration testing, trying to break into the system, is probably the most important phase of the methodology. It determines whether we set ourselves up for success or failure. So maybe I know the name of the file in question. So the type of information I want to gather and the questions I need to answer include the following. Is the file an executable? Is it a binary? Do we have malware that are not executable files? Yes. What? Word documents with macros enabled. Yes. That was exactly the one I was thinking of. We can also have just emails, which can have things in them. So then we say, is the file binary? What architecture was it for? That's an interesting question. I have a new MacBook Pro. I was doing some binary analysis of the executables in there. They actually contain both M1 architecture and Intel architecture executable code in the same binary. So they can ship one set and then the machine, depending which processor you have in the MacBook Pro, as they're making the transition from Intel, which one's there. That was fascinating to find out and terrifying. Just like when they first came out with the NTFS, the file system for Windows, there's multiple bands of data. And so you have your regular data band, but then you can have an out-of-band data for other stuff and people hiding things in there at first. Why not? Because you can. Okay, for which architecture was it filed? What is the format of the binary? If you're using Linux, most likely it is ELF. Executable and linking format. Windows uses PE for program executables, I think.
Portable executable.
Portable executable, thank you. The A.out was an older format that Unix used. Is the binary script of its symbol table. When you build a binary and compile it, usually there's information about where all the functions that are in there, what the function names are and some other stuff. You can actually force it to put additional information, debug information. When I ship my binary, I don't want all that extra stuff in the binary because it takes up space. Plus, I don't want somebody easily reverse engineering my code, so we strip it of the symbol table. Can I identify any useful strings in the binary? You can't strip those out because program that runs, which says something like, please enter your name, that string has to exist somewhere in the program. So maybe that's something we want to look for. Is there a running process associated with the binary? Is it already executing in your system? What is the hash of the binary? And SHA or any hash? Because maybe, so there was a program, it probably still exists, called Tripwire, that would take system programs, do the hash of them, and then check if that hash ever changed. Oh, somebody infected your program and changed your program, potential. Or maybe the hash comes back as a known malicious file hash. There are repositories out there of hashes of known malicious files. There's repositories out there of hashes of known good files. Standard, oh, here's the standard distribution, all the MS Office stuff and everything. And here's the standard hashes for them, so you can check. There are hash databases out there of child pornography. So you don't have to look at the pictures. You can just scan and check the hashes. That's actually a good thing. There are lots of ways of changing things, though. So the hashes, especially things like images and stuff, you can easily modify an image slightly so the hashes don't match anymore, and yet the image still looks the same. Executables, yes, you can do that too, but you don't want to. Unless you're malware, you want to change it all the time, change those hashes. Can we identify any useful function names? And we'll come back to that one. Identify any libraries the program uses. So that was something that was mentioned with the life and the day of the cybersecurity analyst. They were talking about, hey, see if they use this toolkit, see if they use these libraries, because then we know something about it. When was it written to disk? Who modified it? When was it modified? Is it old? Is it new? Can somebody lie about that? And the answer is yes, sort of. Yes?
It's actually the file encoding. You'd have to hack it.
It's in the file system
Yeah.
data. So you have to have root privileges and hack that. Or you just change the clock on the system and rewrite it. When I was an undergrad, I was working for a faculty member who bought software that expired December 31st of that year. So he had me reset the system clock back a year so he could use the software for another year. And it wasn't connected to a network clock or anything. We're talking, oh God, that was probably 85, 86. So for a non-malicious binary, such as an application developed within your organization meant to run on Linux, you can ask similar questions, but in a more targeted approach for vulnerability analysis. Hey, this is something we don't think is malware, but something we want to check. So does it take any input, user or otherwise? If it takes user input, you want to make sure it processes that user input in a safe and secure way. It doesn't take that input as if it was a piece of chewed gum on the sidewalk, pick it up and throw it in its mouth and just start chewing. It sanitizes it. You want that. Okay, that was disgusting. But so does it validate all input? Does it safely manage memory? Does it use up-to-date libraries or third-party frameworks? How is it compiled? So there's actually a DARPA program right now where they're worrying with their concern was we have legacy software, old software running on US military systems. We need to update it because they used an old library and that library's been updated. We no longer have the build script. We may not even have the source code to the original tool. We just have the executable. How do we do a binary analysis of that software so we can figure out which pieces of it are the functions from the library that got updated and then update it correctly? Are there any noticeable strings containing sensitive data, such as hard-coded passwords? Nah, that would never happen. Paths to special files. So these are all things we can look at. How do we do this? So if you're still in a root shell, exit. I want you to download, if you're willing, the book files. It's not very big. So can anybody tell me what wget stands for? Yeah. WebGet, yeah. It basically, instead of going to a browser and searching for this and hitting download, you just use WebGet and it just fetches the file for you. It'll be a zip file, you unzip it, and it'll expand it into binary analysis cookbook /master, and we'll change into chapter 4, 64-bit. So what he has in his different chapters is both 32-bit and 64-bit compiled executables for different test cases. So I know this will take a little while to do, so to type. And remember, if you type it wrong, you use the up arrow to get to a back arrow to back up and retype that once, followed out after retype the whole thing. I was able to cut and paste it, so I didn't type it. That's all one word, by the way. So after the slasher, if there's no space, you just start with archive. Or one string, I should say, one line. Anybody get it yet? Good, a couple people. Anybody still typing the command? See 1, 2. Everybody got it? Anybody not have it yet? Okay. So in that chapter 4 directory, I want you to do this file on chapter 4 example. Oh. Yeah. They're meant to be small to make them parsable. So I'm going to clear this actually. So I did this, and then the other one I said is actually do, so go up to the parent directory, go into the 32-bit subdirectory and do that. So he has, like I said, both 32 and 64-bit. Notice the difference in this command between the 64-bit and the 32-bit. 64-bit says it's in a 64-bit executable. This is a 32-bit executable. So this is just Intel 8386 version. This is x86 64-bit. So just, he has both 32 and 64-bit. You can look at those. We're going to stick to the 64-bit for now. Why? Because that's where most things are going these days. If you go into embedded systems, there's a lot of 32-bit. And I talked to Schweitzer. It's like, you know, they're talking about process. You know, we're like, well, how fast do you have to go? And it's like, you know, 10 times a second. You know, a process, we don't have to have really high speeds to analyze things. So, all right. So type the first command, and you might want to do the more on it. Strings, chapter 4 example. I'll go to that. I'm going to send mine through more so you can see there's lots of strings here. Actually, how many are there? 85 strings, so not a whole bunch. But you notice here it has things like, please enter the password to unlock the hidden message. The hidden message is, oh, that's a format string because this is part of a format string for the command. Wrong, run the program again. So if I actually try to run the program, it says, please enter the password to unlock the hidden message. I'll type password. It says, wrong, run it again. But strings, so strings is useful because it gets to show you all the strings it thinks about in there. Now notice some of these, I'll talk about these. These strings are actually names of sections in the executable. They have nothing to do with the program itself. These strings are the names of dynamic libraries, things that are in shared library executable names. They're things your program calls, not necessarily, you know, there's main, there's a function name for my function. Oh, hey, apparently there's chapter 3 example.c. I have no idea where that came from. CRC stuff.c. So this thing is unstripped, so it has a lot of different stuff in it. We'll come back and look at some of these. But strings is a very useful first pass at looking for files. You want to look for things. Okay. I'm going to go on to the next command. I'll come back to this. We also have a program called readl. Reads the executable linking file, the format file, and different options. So -H shows headers. We got these different ones, -LW, -capital SW. The next page has -lowercase SW. Just look at those, see what that's showing you. So I'm going to go back. Read L -L. So this gives me some information about the executable. It says it's an executable L file. Entry point, there's the start address of the program. There are 9 program headers starting at offset 64 in the file. And this gives me some information about them. So these are program headers: interpreter, section, load, dynamic. This load tells it this is these sections actually get loaded when the program starts running. Dynamic says this is the list of the entry points to get the dynamically linked files. There's a note. EHRIN, this is for the execution handler. This is read-only data. And notice this, I should mention this too. Program interpreter. When you're running the program and it says, hey, I need to use the shared library, like printf from the shared GLib library, how do I find it? How do I get it? It loads this, it tells this interpreter, here's the name of the library I want to get loaded for me. That becomes an interesting, hard but interesting thing to attack with. Because I could change this if I could modify your executable. There's some other things I can do too. Then there's we have segments. So these segments up top here have different sections. So we have an interpreter section here. We have a bunch of other sections that are or segments that are in the file. Okay, so what was the other one I did? Let's see, -H. So this shows us more information about it. There's the -H. Magic number. So magic number is usually a number in a file, usually in a file that tells you the file type. Character 7F followed by ELF2. If it's a 32-bit file, it's character 7F followed by ELF, uppercase, ELF1. 30, so 1 is for 32-bit, 2 is for 64-bit. It tells it it's a 2's complement little endian number format. That's what this one is for. Version 1, Unix System 5, application binary interface version 0. It's an executable file. Then the machine AMD, so 64-bit Intel. So they use the AMD one. Why do they say AMD instead of Intel 64-bit? They publish their standard first for 64 bits ahead of Intel. Entry point address, start of the program headers, start of the section headers, flags on it, size of the headers, etc. So we get some additional information here. Let's see. Capital S. So here's all the section headers. And I don't like this format. There's another format I like better. But notice there are 31 section headers in here. So the null section is 0. Then we have an interpreter section, a note, the AVI tag, note, GNU build ID, GNU hash, dynamic symbols, dynamic string, version numbers, relocatable dynamic, program linking table, process linker table, excuse me, initialization, etc. Text is actually where your code usually goes. Initialization, finalize will show that read-only data, exception handlers, initialization array, finish array, etc. There's a lot in these programs. Your compiler and linker loader builds all this and puts all these bits in here. And a lot of these aren't very big. If we look at the size, you know, this is 1C, so a little less than 32 bits, bytes, excuse me. We go down to, you know, none of these are really big. Actually, none of these are big. Text maybe here. Let me go to pick a different program, bin/ls. And so here the text size is, you know, a bit bigger. So address tells us where we want to load this in memory. It's this big, and this is the address. It's the data for this section starts in the file. So we can take this ELF file go and say, oh, give me just the text section. And it'll go and say it starts at byte 28B0X and goes for F198 bytes long, and you can download it. And so I have tools that I use that do this. They grab the data for each section, the read-only data, et cetera. I should mention the .bss session. I like this. Notice it has a type called no bits. Program bits are, hey, this is code. No bits, it tells it started at this address, at this offset, it's in the file, for this length. Notice the next thing's at the same offset. BSS says reserve this amount of space for zeros. And we'll put global data in there that is uninitialized, just with zeros, it's not preset with any value, up in that space when we allocate. So it keeps the executable smaller. We don't have to say, hey, we have all this global data we need space for. We're not going to initialize it yet. Take up space on the disk. And here's some flags. So A means allocate space. X is it's executable. W, this should be writable when it's up in, when you've loaded it. Some are not writable, like the text section is not writable. You allocate space for it, you make it executable, but you don't let somebody overwrite your code.
Yeah, found the buffer overflow exploit in their program.
It's not my program. And yes, there is one in there.
Yeah, you're using scanf with %s.
Yeah. No, that's from the book. It goes to that one later. Did you find the hidden hard-coded password?
I didn't check for that. I was looking step by step. I'm like, okay, you're scanfing, where you're going to try and compare that to the string. I'm like, oh wait.
So run the program. Guess the password. Win. Get the password. I'm going to step down the hall for 5 seconds while you do that. Okay, maybe more 5 seconds. How would you even find that? So there's a password in there it has to check. It's not encrypted. How would you find it?
Probably one of the strings.
Strings. You would look at strings.
Yeah.
That's a good way to do it, unless they hid it somewhere.
Yeah. So I've got 2 strings that probably.
Well, try it.
But
Run chapter 4 example and see. And now I got to see about your buffer overflow. Yep. I'm pretty sure he had deliberately had one in there. I've got my own in a different example. I thought you'd get it. So if I can type in, I tried this one already, password, it fails. My first password ever used, Trousap, password spelled backwards, because I thought that was so smart. That was over 35 years ago, so. Anyone find it yet? One, okay. So should you ever write a program where the password is written into the code so that it can't be changed? No. Do people do this? Yes. Sometimes what people do is encrypt it and store it in there. But there's still ways of trying.
Make me remember a stupid project that involves web development. And the idea was to create some sort of system for a library manager to deal with their computer, right?
Mhm.
We had one person who said they wanted to do the front end, and they never actually talked to us about the back end for it. So we ended up writing the front end, right? And after we complete this thing, she tosses out her front end, which does its own version of password handling in JavaScript, and I'm like, no.
Yeah.
I have a system. It uses script, and it does password management.
Anyone else get it? We have one. Did you get it?
Yeah.
Two. Anyone else? You want to keep working on it, or you want the hint? Strings. Look here. That's close.
Let's see if I can find it by.
Now I'm going to show you a different thing. If I move in the directory, I can look at the source. That's written in there in the source code. So if you have the source code, it makes it easier. Hard-coded password with some capitalization in it. And the hidden message is a little harder because they used it, they used a macro for it, but they didn't try very hard.
It actually had like H at like the front and the back of that, which I found.
Yeah, the H's were interesting. I found that interesting too.
Yeah.
Let's see.
Silly. I was trying to see if I could like find where it's pulling from.
Oh, right.
I saw two strings there. I'm like, okay, maybe one of these is password. So I was looking through the
I'm trying to see if I can find it.
the assembly, and I'm like, okay, so where are you doing stir conf? And it's actually checking against some place in memory on the stack. And I'm like, okay, so he's not like pulling off some place in RO data and then comparing it against what he read in the scanf. Instead, he built the string on the stack to
Oops, password.
make things slightly more.
It's interesting. And it's like when you look at the C code, though, it's just straight in there. So it is interesting how the compiler modified it slightly.
Actually, I know why that is. So it is wanting to work with registers as much as possible. So
Right.
it loads the string into instructions. It's coding it into instructions. And each of those things has to be
Yeah, it's an optimization.
bytes.
It's an optimization thing. Programmers, compilers do really interesting things. You got to play with the code and see what they're doing. Yeah, so it encodes it as an instruction, so it can be loaded as an 8-byte value. It's a little weird. What's interesting is it means it's not doing what you expect it to do. All right, and that's the key to a lot of this stuff. Is the executable binary, the compiled version is not what we teach you in the intro programming classes or the intro compiler class. Things are not what they used to be. So there's a bunch of other commands we can use for readelf. Readelf is just one of the tools. And what these are doing is the middle three are just looking at the program section, the text section, and looking at them, but looking at it in terms of raw data. I don't like looking at it in terms of raw. I like looking further, so we'll take that in a second. The string table, there's another way of looking at that, so I will do that one. readelf minus p dot string tab. And this is all the strings and their offsets. So again, CRT stuff, etc. These are strings used by, I need to be careful. These are strings used by the ELF file, not necessarily by your program. So they're not the strings of your program. They're the strings the compiler created. So these are the names of the dynamic libraries that it called. These are names of functions and other things in there. Okay. So that's an important one to understand. It's not your program strings. Oh yeah, so if we do the -x for hex, I should do that one with text version. Dot text, excuse me. You can see here's the program. And the one thing that he was pointing out here, so you can see in the middle of the text section is an hard-coded password. They actually took the data for the string and included it in with the code. It's not in a separate read-only data section. So the compiler optimized it and put it inside the code to try and just change things. If I compiled it with a different compiler, things would be differently. We'll talk about that in a minute because there are some interesting things that compilers do. Is there any questions on this stuff so far? All right. Let's go to the next one. OBJ dump is like readelf, but it's object file dump, object dump, that can do different things. And again, it just puts things in a different format. So if I look at OBJ dump -f, the file, it tells us some information about file format, architecture, start address. If I look at its headers, this is the format I'm used to reading. For the sections, index, name, it's much better formatted. The size of it is here. The virtual machine address, the logical machine address, they're almost always identical. They offset into the file. The alignment, where does it have to start? Does it start on any boundary? Does it start at 4-byte boundaries, 8-byte boundaries? So this is 4-byte, 8 bytes. The flags for it. Does it have contents? Is it allocatable? Do you load it into memory immediately? Is it read-only or writable or executable? So let's see, where's our text section? So text is listed as code for read-only. We go to read-only. Data is read-only. This stuff is not marked read-only. It's data section, so they're writable. And so it shows those headers. What else do we have? Oops. -j. That shouldn't be a minus there, just a dot text. -j tells it pick just this section to look at. Okay. I'm going to get to a couple things first, and then we'll come back to that. If I do an LDD, let's do -b. This says this program uses the standard libc library, glibc version 2.7, and also older versions, 2.4, 2.225. And so these are the libraries it's using. What I liked looking at was, what if I look at, instead of this one, user bin copy, CP, the copy command. It uses a lot more libraries. So libpthread, this is for multi-threading executable. Dynamic loader, pcre, that's for regular expression analysis, standard Lee library, access control library, etc. So you can look through and see all the different libraries these different programs use. And these are things that may be susceptible to attack if you know about them.
Also, to do two different readings of sections. So say I want to disassemble the text section, and then I want to dump the RO data section as hex?
I do them separately. You know, I would do, well, let's do this clear. So OBJ dump minus hex section dot RO data. Oops. My executable. And so the RO data is not very big. Only 80 characters. And it's just showing the data that's in it. I don't like that one. There's something wrong there. Let's see. There's the manual. Let's see. Where's the hex dump? Been a while since I've used that one. I do it a different way. But what I'll show you is what I was going to get to. If we look at the .text section and I use disassemble. Whoops. Obviously, something's wrong here. There we go. It'll actually show you the assembly code for it, right, for the sections. So what I do, to be honest, the tool, because I try to automate this, I have tools. I open up the L file, find the section there, and say, oh, here's the read-only data, and raw read in the bytes from the file myself into an array, and then I play with it. I was, with our tools, running the OBJ dump with the -d disassemble, not showing this data, the raw instructions, I pulled that out, and then parsing this. As of last week, I'm now using the lib opcodes library that OBJ dump uses and calling it directly and saying, hey, just disassemble this for me as you go one step at a time. There are other libraries out there like Capstone. There are other libraries out there that'll do disassembly for you, and you can say, hey, disassemble these bytes. And it's opportunistic and disassembles as many as it can until it says, that's the end of the instruction. I'm going to return. I disassembled, 2 bytes, 3 bytes, 1 byte, or, depending on what these instructions are. And no ops get interesting because you can have 1 or more bytes, no ops. So it's becomes really interesting. Now, if you can read assembly, you'll see what this does. If you can't read assembly, it gets hard. This was the start address. So this is where it actually starts. It clears out the stack frame pointer. It does a bunch of other things, initializing some things, and eventually calls libc start to initialize the dynamic library, the libc dynamic library. And that one will then call your main program. So it actually does some initialization, does some other things before it actually gets to your main program. Let's see. Actually, let me do this one. I'm pretty sure, well, I'm not sure. So this has a start, also libc start, but this is all now. So Intel, it's ESI for 32-bit registers, AX, RSI, whatever, for 64-bit registers. So obviously this is all 32-bit in this one. I love this command, get func. What you do is you call it. It then takes the return address and stores it in the EBX register and then returns. Because in 32-bit Intel, there is no instruction pointer register. 64-bit has an instruction pointer register, 32-bit doesn't. So the only way to know the instruction, the current instruction pointer, is to cheat. So you call get func, or you just call the next instruction, that works too, and then pop it. So this is a common thing that shows up on almost all 32-bit things. When they want to have position independent code, they do everything relative to the program counter. They store that program counter in the EBX register so that they can do the math. Little things like that that you learn when you're playing with this stuff. So let's see. There's main now and stuff it does. I'll come back and talk about some of this in a bit. Hex dump, oh yeah, I didn't do the hex dump. Hex dump minus capital C says show the hex values in the file followed by the ASCII format of them. So we have the hex offset. So you notice here, here's the magic value. This is the start of the file, character 7F, and then ELF for ELF. So you can actually go through very carefully. This was the start of the dynamic loader program, etc. Here's the names of some of the functions that we're using and what library was using them. This is hard to go through. Notice the strings. Hey, please enter the password. A lot of this is code, which you can't really read this way, and that's why we need to do the decoding it this way. Decoders, disassemblers are not always correct. Why? For Intel, I should say for Intel.
Okay.
Yeah, you can tell here, look at this. This is a 2-byte instruction. This is a 3-byte instruction. This is a 7-byte instruction. Intel instructions can start on any address. So here it's starting even, odd, even. Actually, that one's even. Odd. It's starting odd. So you can start anywhere and try and decode it. This is one thing attackers use, is they can say, hey, I'm looking for, let's see, the return instruction, which is C3. So I'm gonna, here's C3 for return. I'm gonna look through all this code. Well, if I could possibly find a C3 somewhere in the middle, I could tell it, hey, start here at FD and decode that. I can cause it to jump here. This might be a completely different instruction. That makes this really, really hard and hard to analyze. And that's where you need automated tools to help with that. One I was dealing with recently is this in the back. If we're looking at stuff between functions, some tools do padding, some don't. The one I was using was putting pure zeros in, which is not a no-op in Intel. And so the disassembler was saying, oh, that's an add byte 0 instruction. And it was offsetting and it wasn't finding the next function correctly. And it was like the next 20 instructions were wrong before it finally got resynced.
So if you had GDP, couldn't you tell it to debug for a specific address and therefore get different?
You can tell it whichever address. You can, yes, you can do lots of things. And with the disassembler, like I said, I'm using the libopcodes library or Capstone. You could do that. You could just say, hey, start disassembling here. This wouldn't be a move 0. This would be a add byte 0, actually. Now, one thing I'm showing you here, a lot of you may be looking at this and say, this doesn't look like Intel to me. I'm gonna, let's see, minus capital M Intel. Okay, that's wrong. Obviously, I did the version wrong. I never use this. So, is it little m? No. Little I, maybe. It's supposed to tell me. No, yeah. Notice it's using things like double word pointer and these square brackets. So Intel standard notation, let's look at this last one here, right? ESI plus EIZ times 1 plus 0 hex. If I did that without the Intel one, let's see, that's right before register TM clones. It was using this notation. Okay, so let's see. Rep 804, 845C. So yeah. That one, and then do the Intel one. These are the same instruction. This one is an AT&T syntax for Intel. This is an Intel syntax for Intel. This syntax shows you things where the destination register is last Intel, the destination is first because destination equals the source. Here they say copy from source to destination, except in the subtraction instruction, it's the other way. This is an array access. It says take this base register with this index times this size per each one. So they're just, it's an array of characters, offset 0. So take the value of ESI, off, index IZ of 1, give me the address of this and store it in ESI. That's now a pointer to a character in that array. This is the exact same notation. A lot of people are taught to read the Intel notation. I grew up on the AT&T syntax notation, so I never do that one. Sometimes, and I don't remember which one, these opcodes, the instructions, are spelled differently between Intel and AT&T. Some of the classic ones. The modern ones, any new ones Intel added, how many does Intel have about now? About 1,500 different opcodes. The new ones they've added are the same, but the old ones use the old. So it's you have to figure out what notation you're using when you're doing these things and play with them correctly. So that's always fun. I wrote my tool using the AT&T stuff, and now my students are like, I can't read this. I don't know how to tell them. It's my tool. You got to learn my way. All right. So, oops, how'd that happen? Back to the first slide. Okay, so the static analysis, this disassembly I'm showing you here. What I usually do is I'll run obj minus d, that means disassemble. Capital D says disassemble every section, lowercase d says disassemble only the code sections. And I store it in a file. Why do I want to store it in a file? Because I want to browse through it back and forth, and the last thing I want to do is use more to go back and forth through it. They're big. And this one was supposed to be, I don't know why I have it twice. Okay. So let's look at, I'm going to look at a different example than what they did. Here's this code for this example. Really simple. We have a function foo. We have a function name calls foo. It has a buffer overflow before somebody says, so enter your name. I read it into this buffer. The buffer is only 20 characters long. It also adds, it does a loop. That was the original thing, and then added the buffer state later. And so let's play with this a little. I'm going to try some different things. So my code's in here. So enter your name, Jim. It says, hello, Jim, and the sum was 18. I can enter my name. Well, actually, let me compile it. Let me make sure I'm doing this. GCC temp.c out or temp1. Output temp1. There we go. Make sure I'm running the right version. I could type beyond 20 characters. And we get the segmentation fault, core dot. I did a buffer overflow. I crashed it.
I've got smashing tech.
If, depending on the version of GCC you're using, depending on the version of Unix you're using, it may default to using -f stack protector. This is an option in GCC. And now if I run this, it says stack smashing detected. So in my intro software security class and how to program stuff, we give them examples of how to do a buffer overflow attack. And it fails now on some versions of the compiler because it has stack smashing detection enabled where others don't. Okay, so actually let's look at this. I have it in my slides, I think. I compiled this 3 different ways. One, using the normal default compiler for this version of Unix, which is AWS Unix. I then did it with a stack protector, and I did it with something called Fortify Source. And the -O is an optimization, it's turning off optimization so it can fortify the source. And I stored it in 3, then I did an OBJ dump and stored it in 3 different files. So, normal code. This is function foo. It stores the stack frame, copies the call frame, copies the stack pointer into the call frame pointer, allocates 30 hex, so 48 characters of space on the stack, copies EDI into a local variable on the stack. What's that? EDI is a register and it's putting it onto, now why do I know it's a local variable? One, it's, I guess I should have, where's my, for those who don't know how these work. We normally have our stack, the old call frame. We have the return address pushed on the stack when we make a call. Then we push the RBP register. Now, RBP is then pointing to here. And then below this is where I allocate space for the local variables. Okay, so these are RBP minus something gives us access to the local variable. So RBP minus hex 24 is where I'm storing something. In traditional communicate stuff and 32-bit compilers, the parameters for a function are passed and stored on the stack. In 64-bit compilers, most of the parameters are passed in registers. So EDI is the first register that is passing the parameter. It is not on the stack ever. Now, we have a set of 6 registers that we can pass things on, not on the stack for normal integer type things. We can use the XMM registers to pass floating point numbers, not on the stack. And then we put the rest on the stack if we pass way too many parameters. And there are different calling conventions doing this. So Intel invented their own. This is now the standard 64-bit one. 32-bit stuff pushes it on the stack. So when we tell you, oh yeah, you're doing stack smashing, your parameters on the stack, you know, maybe. The other thing I want to mention is this is the one of the local variables, right? So if I go back to my code, this is function foo. Here's integer I. It's passed as a parameter, but now what I'm doing is I'm storing it on the stack. Notice here, I have K, which is a certain size. I have result, or res, which I'm using for result. I have my buffer. The compiler actually allocates extra space to store the passed parameter on the stack because it needs some place to put it. That's a common thing. It may need that register later, yes. So it saves it on the stack. Now, here's an interesting thing. Depending on the variant of the compiler you're using. So in Ubuntu 20.04, using the latest version of GCC, it puts this array, this buffer, at the top of the stack above K in res. Older versions of GCC put them in the order you see them. The C-line compiler puts them in the order you see them. So even things that I program the way I expect to see them when I'm doing the binary analysis and looking at things, it doesn't directly match the source code. The source code will move and rearrange these things. How annoying is that? Okay, because
Put in the statute flag.
But what if this is somebody else's code? They didn't compile it with the JASG flag. They stripped everything out. They turned on full optimization to really mess with me.
Well,
I assume everything was compiled with full optimization and everything was compiled with no debug data, and I want to do binary analysis of that. So that's where I'm playing. Now, this is the normal code. Let me actually see if I can erase all these marks. By the way, there's some good additional information, nsacodebreaker.org/resources on interpreting and reading Intel stuff. NSA does an annual code breaker challenge, free to use, free to do. And this is just part of their tutorials that they have for that. Now, on the stack protector, things are different than this other code. I've highlighted it. What the stack protector does is it finds this one value, I'll explain for this in a second, stores it in the RAX register, and then puts it as right below the base pointer. So the top thing on the stack right before your return address, well, you have return address, RBP, then you have this value stored. Then what it does is at the end, so ... At the end, it copies that value into this register and compares it with what was in memory. If they're the same, you're good and you can leave. If they're not, it calls stack check fail with standard library and said, stack smashing detected. Why? Somebody's buffer overwrote the special value, this one called stack canary value, which is a random value. When the program starts, this value is randomized. And then if you overwrite it, you overwrote it with the wrong value, probably. It's a 64-bit random value. There's only a lot of those. I don't remember how many. I know 32-bit is 4 billion. So
That value is hard to put in the instruction.
I'm sorry. No. FF is a segment pointer. So back in the day, for protection, they thought, hey, what we're going to do is we're going to break up memory into segments, code segments, data segments, stack segments, etc. We're going to have a register pointing to the beginning of that segment. And then we can add to it an offset. So 28 bytes, hex bytes into that segment is where we're going to store this value. And so this FS value is initialized when the program starts. I don't know what it is. I haven't looked. Almost nobody uses segment registers anymore. They're using a few special cases. Most programmers and compilers said, oh, we're just going to call it a flat address space and have everything start. All segment registers line up in the same place and everything starts at the same place. We'll just go from there. Because that's the C programming model, so why not follow it? I'll tell you why, because C is security dangerous. All right, so this is, it calls stack check fail. Now, the other program, you notice, this didn't call stack check fail. It didn't do that special stuff. It moved this register into the stack. Actually, this one, I should clear this, make it a little easier to see. Also moved this register, but it's a different location on the stack. Why? Because it needed the extra bytes for the stack protection. So it's a stack canary. It's an old idea, a couple decades old, but it works. All right, what else can we do? The fortify says, hey, we know you're calling printf. Well, printf is a dangerous function. So we're not going to let you call printf. We're going to call printf check. We're going to pass a couple, the compiler will force it to pass a couple extra values. So we do have the stack pointer in 32-bit, in 64-bit. So we take the stack pointer and pass it in register RDX. We pass the actual pointer we're doing for printf here. We tell it how many arguments it's supposed to have. We pass that all to printf check, and it tells us if there's a problem. And so you can fortify your source, and this is a default again in some versions of compilers. And all you call is printf check, scanf check, and all these check things that make sure that you weren't breaking the rules and overflowing the buffer intentionally, accidentally. So it's nice. The compilers have started building in all these protections of things that we're concerned about. Why? Because we can't protect programs. We can't trust the programmers. We have to protect them against themselves. So just looking at this, I mean, this was a fun thing when I was looking at this because you can actually see how it changed the code. Now, this one I could also done fortify and stack protector. You would have had both in there. And if we look back at let's see. 64-bit. So this one that he compiled has a main. And I'm noticing it just calls printf. So it doesn't have that default put in. And if I can look at the end of the function, I do see a stack check fail. So it's using stack protector, but not the fortify source. And just doing a search of the libraries, I can look at things like this. I'm going to actually do my standard, not the text. The way I like reading these things, I do is mine is PDFH. So I see the program headers. I see all the different dynamic sections, their offsets, the version references from the library, the section headers, disassembly of section init. PLT is the procedure linking table. And this is how you call dynamic libraries. How does it work? So I call this address. It jumps to this location, which is actually in the GOT table, GOT, global object table. That address, the first, it's initialized to have it call, jump right back here. They push 1 and then jumps to this PLT address 40E0, which is the start here. And what it basically does, it says, hey, call this dynamic linker, find the address of this function I really want. It's function 1, and this is in my dynamic symbol table. So function 1 is printf, and store the address for it here in this address. So, which is technically, when you do the math, the instruction pointer plus this, you get this. Store it there. So the next time I call this, I jump to the contents of this, which is the actual real start address of the dynamic library. So it dynamically loads these each time you're going, does a search, find these, and puts these in. Because of that, it needs to know the names of the functions, so it can pass it to the glibs, the library thing, to look it up. So all of these functions, like printf, like libc start main, etc., those names are in your dynamic table. You know every single dynamic library that this calls. And that is a good thing to figure out. And you can look and say, oh, hey, I saw it called scanf. Scanf is a dangerous function. Let me see what it does with it. Oh, it's called scanf check. I can't do much about it. It's going to do it right. It calls nscan or scanf or nscanf. I don't remember which one that is. Which you're supposed to tell it this number of bytes, maximum number of bytes. So there's a story back in, I want to say 2005. Somebody who worked for Microsoft said he was, they had a buffer overflow attack. Microsoft back in the early 2000s shut down all their development and did massive training of all their people for security. They put together a standard that says from now on, when you pass a pointer to a buffer, you're going to pass the size of that buffer next with it. So there was a buffer overflow attack against new code. The guy in charge of security was called into Bill Gates' office. Bill said, so tell me, who wrote this bad code and why is he still working for me? And the guy said, it's not his fault. And Bill said, yes, it is his fault. We had this training standards. We know. And the guy said, no, let me explain what happened. The guy did everything he was told to do. He said, he passed in the pointer to the buffer and the size of the buffer. Using Microsoft best practices, he actually didn't pass in the size of the buffer. He passed in a macro value, a defined value, buff size, or max buff, or whatever it was called. Because that's Microsoft best practices. I'll come back to that in a second. He compiled it and tested, did his unit testing, loaded the include libraries, did all the tests, everything worked, submitted for the build. The build process changed the order of the include files. Both two different include files define the same macro buff, max buff at different values. Actually, that's not quite what happened. So the function he was calling used one macro to define the size of the buffer, and the thing that actually allocated used another. So basically, they defined the same macro value, two different places, two different sizes. So the place that allocated the buffer was different than the place that used it. So they fixed that. No two header files shall have the same defined value or the same name defined value. A friend of mine, a faculty member, former faculty member at University of Idaho, did consulting for Microsoft in 1992 and told them that was a bad practice they were doing. And they needed to fix their best practice by using macros for everything, especially because they didn't have this. They fired him instead of listening to him. It took them 10 more years to finally fix it. So these buffer overflows happen. Even when people do best practices, we're passing the size, we're passing this. We could be wrong. So we have to be careful with that. All right.
Problem that C++ would have fixed. Instead of using macro, you can use the context for size to value. Because it's a variable, if you define the same variable twice, it's going to go,
Right.
buddy, stop that.
But people like macros because they're easy. So anyway, that was that one. All right. There are other tools out there. I'm going to go over one more. NM just looks at some names of the libraries and stuff. OBJ copy allows you to copy parts of an object file, an L file to another part. strace and ltrace, they actually, let me go that one. So I'm going to do strace, system call trace. And I'm going to run the example. And these are all the functions and system calls it's called. File stat, check the status of a file, close, open at. So here it's opening the library, reading, etc. mmap, so allocating memory, protecting the memory, doing all this. Finally gets down to running my program. Does a write, please enter the password to unlock. And now it's reading, it's waiting for me to type something. So I typed in Jim and then said wrong calls. So you can see every single system call it makes and the values of the parameters and stuff. ltrace is something similar for calling libraries. And so there are tools out there to test what it's doing. That's cool. There is a great tool out there called GDB. GNU debugger. So I'm going to set breakpoint for main and tell it to run. It runs until it gets so far, then it stops. I can now look at the value of registers, and it tells me what their values are. I can look at the call frame, and it gives me information about that. I can step through instruction at instruction, and it goes through and does different things. I can disassemble the instructions. I can look at them. If I have debug enabled and debug code 0 will show me the C code that is executing. There are some libraries, Python add-ons that you can use to GDB that are really good for disassembly. They give you a lot more information. They print out the strings on the stack, etc. So this one's not going to work because this is his code. Or I could just tell it running. Program is being debugged, started from the beginning, yes. There's even a way of having to record every instruction. So you can step backwards through the instructions and undo things one at a time after a crash, which is a common thing I like to do when it crashes, figure out where it broke. There's a lot you can do with GDB. It's probably more in depth than I want to talk about right now, but it's a very useful tool. It's not as good as I had a nice GUI one when I was growing up. And we had the debug interface in one monitor, which was the text monitor, and then the program running in the graphical monitor. That was way back in the day. You had a text monitor, graphical monitor, because you couldn't do other types of double monitors. There are a lot of different tools out there that exist for doing debugging and other things. So I went a little faster than I expected. So any other questions? So these are just some of the, and all these are standard tools available, built into Linux. And some of them are available in Windows too, like OBJ don't install in Windows and do things. Or in Linux subsystem for Windows. Have people ever used that? Ubuntu for Windows. I love it. So I can do quick little coding things while never having to start up a VM and never leaving my machine. But special little things like I can just do a remote shell, secure shell. I can do FTP, secure FTP, other things from there. I can whip up quick demos when I'm talking to my students about something. I did that yesterday with a Linux subsystem for Windows. It's actually pretty useful. So actually, I'm done. I ran out of slides. Other questions? I should have given you a break halfway between. Now we got what, 20 minutes for the next one? Yeah, unless somebody has other questions. Brains all on fire? I told my wife, she said, don't tell this joke, I will. I said, well, if you feel like your brains are on fire, tell them this is like drinking from a fire hose, so should put it out. No, see, she was right. Don't tell that joke. She said, what are your dad jokes? Say it again. Yeah. Well, I said, after all this time, people feel like their brains are on fire. Well, this talk was like drinking from a fire hose, so should put it out. So, yeah, see, it wasn't worth repeating. Yeah. Oh, thank you. You want me to pause this?
Yeah. No pause.
Just let it go? Okay. So anyway, the slides are available. Everything's there. The book's available. There's lots of different other books and tools out there. Google Cyber Grand Challenges. Let me tell that story, actually. Yeah, never mind. I got time, yeah. I don't know if people want to hear it. So.
Okay, couple announcements or